This video is the third in a short series on antiderivatives and indefinite integrals, and our goal this time is to learn how to calculate indefinite integrals of power functions. So there's the indefinite integral of a power function, and we see that a power function means x raised to some power. And notice that whatever the answer is, we have a plus c attached to it because the indefinite integral is the most general antiderivative and it comes with an arbitrary additive constant. Now we already know the rule for differentiating a power function. So when we take the derivative of x to the n, we bring down the original exponent out in front, we subtract 1 from the original exponent. And what we're trying to accomplish here is to do this process backwards. And we can figure this out by basically guessing and adjusting. So we set up the integral x to the n dx. And the antiderivative here means the thing you differentiate to get what you see inside that integrand. Well, to get an x to the n out of the power rule, I must be differentiating something times x to the n plus 1. That's the meat of the answer. And then we just go ahead and think about what would the derivative do to x to the n plus 1. It would bring n plus 1 down in front and then subtract 1 from the exponent, giving me an x to the n. In other words, the derivative of this is n plus 1 x to the n. So x to the n plus 1 misses by a constant. All we have to do is put that constant out in front in the denominator as a 1 over n plus 1. Now when we differentiate this thing, the n plus 1s are going to cancel and I'll be left with just the x to the n. And of course, we don't want to forget our plus c. So there's our basic formula for using the power rule backwards. In other words, getting an indefinite integral of a power function. You add 1 to the exponent and then divide by the same resulting number. But we have to be careful here to note that there's one value of n that doesn't work, and that's -1. Putting in n equals -1 into this denominator would cause division by 0 and the result would be undefined. So we make a note on that. This only works if n is not equal to -1, and we'll get into the n equals -1 case on the next slide. First, we're going to work a few examples of how to use the power rule. In the first example, we're asked to find two functions, capital F of x, such that f prime of x is equal to x squared. In other words, these capital F's are antiderivatives of x squared, the thing you differentiate to get x squared. When we apply the power rule to x squared, we simply add 1 to the exponent and divide by the resulting number. So in my first answer for an antiderivative, I could just say it's 1/3 x cubed. We just added 1 to the exponent divided by the resulting number. Now what I've done here is choose c equals 0 for my first antiderivative. The second one is found by just choosing some other number for c, and it can be whatever you want. So I'm just going to make it a 5. So there's two unique functions that differentiate to x squared. In the second example, we want the indefinite integral of 1 over x to the 5th. And the key to this is seeing it as a power function. 1 over x to the 5th is x to the -5. So we have the integral of x to the -5 dx. To get the antiderivative, we just add 1 to the exponent. That gives me -4. And we divide by that number, -4. So I have a -1/4 out in front. And we have our arbitrary constant plus c. Now that's probably not the best way to write the answer. It's a little nicer if we put the x to the 4th back into the denominator. And I get a -1 over 4x to the 4th. Plus c. In the next example, we want the indefinite integral of 5 dx. And this is one that you could probably just guess, but we're asked to show it by using the power rule. So the integral of 5 dx, we have to see this as a power function, but there's no x in there. And the key is that 1 is x to the 0, and 5 times 1 is the same thing as 5. So I have 5x to the 0 dx. So the 5 is a spectator here. And then the antiderivative of x to the 0 is found by adding 1 to the exponent and dividing by the resulting number. So x to the 1st over 1. Of course, the 1 doesn't do anything there. And so we end up with a most general antiderivative of 5x plus c. Finally, in our last example, we put together several terms in a linear combination. And we know the integral of a linear combination is just the linear combination of the integrals. In other words, all these constant multiples are just spectators. So when we apply the power rule to the first term, the 3 is a spectator. We add 1 to the exponent, so I get x cubed. And we divide by that resulting number 3, and the 3's are going to cancel. In the second term, the -5 is a spectator. And we view 1 over x cubed as x to the -3. That gives me an x to the -2 over -2 when I apply our power rule backwards. In the third term, we just have the antiderivative of 2, which is 2x. Then we just have to clean things up a little bit. The first term simplifies to x cubed. In the second term, we have a negative out in front, but we have a negative factor in the denominator, so I get a positive result. And that's a 5 over 2 out in front. And then we should move the x to the -2 back to the denominator. So I end up with a 5 over 2x squared. And my third term again was 2x, and then my arbitrary constant plus c, and we're done with that one. So what about that n equals -1 case? So we're trying to imagine, what do we differentiate to get 1 over x? And there's one sort of most obvious solution. We remember that the derivative of the natural log function gives us 1 over x. But then we recall the natural log function has a domain restriction where it's only defined for positive values of x. So this is only true if x is greater than 0. What if x is less than 0? In that case, the natural log of x is not defined, but the natural log of -x is defined. And when we take the derivative of that, we have to use the chain rule. So we get 1 over the argument of the natural log function, -x, multiplied by the derivative of the argument of the natural log function, which is -1. And the factors of -1 cancel out, and we end up with exactly the same result, 1 over x. So this is a second candidate that works. We differentiate it and we get 1 over x, and this only works if x is less than 0. Now we're not worried about x actually being 0 because that's not even in the domain of the original function. So we have a formula that works when x is bigger than 0 and a formula that works when x is less than 0. And if we wanted to write these two functions all at once, we could just call it the natural log of the absolute value of x, since the absolute value function leaves things alone when they're positive but multiplies by -1 when they're negative. So our antiderivative is essentially the natural log of the absolute value of x, but there's a subtle point lurking here about how to deal with the arbitrary constant part. So I've written the antiderivative of 1 over x as the natural log absolute value of x plus c1, that's some arbitrary constant, when x is bigger than 0, and the natural log of absolute value of x plus c2, some other arbitrary constant, when x is less than 0. And this is the most general possible thing that differentiates to 1 over x. Notice that you can pick different constants for the left and right sides of the real number line when you're defining this antiderivative. Now, in practice, calculus books and calculus teachers are usually a little bit lazy about this, and they say something that's not 100% true. They say the antiderivative is the natural log of the absolute value of x plus c, where they only have one arbitrary constant. And while that does differentiate to 1 over x for the left side and the right side of the real number line, it's not completely the most general thing that does differentiate to 1 over x. So this formula, natural log absolute value of x plus c, that's kind of what I use by default, unless we're doing some very unusual problem where the distinction actually matters, that you can pick different constants for the left and right sides of the real number line. So in the examples, you'll see me use that lazy approach. Our first example is to get the indefinite integral of 6 over x dx. And of course, the constant is just a spectator here. Just to emphasize that, I can factor it out of the integral, and I get 6 integral of 1 over x dx. And we write 6 natural log absolute value of x plus c, where we know in the back of our minds that we could be more general by writing the antiderivative as a piecewise defined function with two different choices of arbitrary constants, but people rarely ever do that. The next example is a cumulative sort of thing where we put together the power rule and this natural log antiderivative. So I have the integral of x cubed minus 7 over x plus x to the 10th minus 3. And the integral of x cubed, well, we just add 1 to the exponent and divide by the result. That gives me 1/4 x to the 4th. The negative 7 over x, well, the negative 7 is a spectator there. So I have negative 7, natural log absolute value of x. The x to the 10th, I add 1 to the exponent and divide by the result. So I get 1 over 11, x to the 11. And the negative 3, that integrates to negative 3x. And I put in my arbitrary constant plus c, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.